Okay, so my name is Samna Aziz. I am a volunteer researcher at McMaster University in the Department of Biomedical Sciences and Engineering, and I've conducted 2 research projects over the past 2 years around biomaterials, and I've presented these projects at my regional science fair and at the Canada-wide science fair, and soon at the International Science and Engineering Fair. So my first science fair project revolved around the redevelopment of a bone cement material. And bone cement is a kind of glue, and it's injected into the trabecular bone, so that spongy part of your human bone, and it's used to fill in the gaps caused by fractures. Normal bone cements are made out of a plastic-based material, and I wanted to replace that plasticky material with something more biocompatible, so something similar to what your real bone is made out of. Basically, your bone is made out of 2 main parts. So you have on the outside layer this dense block-like bone called cortical bone, and that's what you can kind of see on the outside. And then if you were to break this in half or slice it and then look at it, you would see a spongy-like inside, and that would be your trabecular bone. So that's very porous, and that's the bone that I would be injecting the cement into. So my idea was to redevelop that material by using something more similar to what your real bone is made out of. So I made a material out of calcium and phosphorus, which are the 2 elements that your bone is actually made out of. And I mixed them in different ratios to make a pasty material, kind of a glue, that would replace that polymethyl methacrylate plastic material in trabecular bone. The cements that I was creating they're very similar to cement that you might see on the sidewalk. Obviously not the same material, but they start out kind of pasty mixture, and they're laid in a certain way, and then they harden and form a solid substance. And that's the same concept here. So you're mixing 2 materials together with a liquid to create a paste glue kind of mixture, and then it's going to harden into something that you can actually use. So I took my 9 cylindrical block samples and I put them in a tensile strength testing machine. It's called a universal compression machine, and it looks like this, right there. And I basically crushed those samples and measured up how much strength they could withstand. So I would put one of the samples on a disc on that cylindrical plate, and then it would push down on it until it crumbled into dust, essentially. And then a computer program would monitor how much strength it could hold before it started to crack and break apart. Yeah, I was surprised. It was kind of funny because when we were crushing them, they broke apart faster than I thought they would, so I didn't think that they would be too strong. But once you analyzed it, I found out that it did fit into the range of the trabecular bone strength. So that was a nice surprise, I guess, because I was worried a little bit when they were just breaking apart. I've always had some exposure to the medical field, but I realized early on that I couldn't look at blood, so that would be a potential roadblock in a career in medicine. So I found biomedical engineering to be really interesting because I have a bit of a creative background, so I like to draw and paint and sculpt and do all that fun stuff. So I saw biomedical engineering as a way to apply my creative background to working on projects that were focused on patient care. I remember when I was doing my projects, finding an idea for a science fair was the hardest part, but my advice would be to keep an open mind. So you never know where you can get inspiration from, and just in your day-to-day life, look at things that you might want to improve.